Across Europe, the pace of hydrogen development continues to accelerate, moving from research programs into full commercial implementation. Three recent developments, Nel ASA's 40-megawatt PM electrolyzer order in Norway, BASF's new catalyst-coated membrane facility near Frankfurt, and Bosch's commissioning of a 2.5-megawatt electrolyzer at Bamberg, illustrate how production, materials, and end-use integration are advancing in parallel. Together, they show how Europe's hydrogen ecosystem is being built step by step, linking technology, financing, and industrial strategy into one coherent framework. In Norway, Nel ASA announced in late 2025 that it had received a firm purchase order exceeding $50 million for PM electrolyzer systems. The buyer, Hydrogen Solutions AS, or YDS, is developing two projects, the HyFuel facility in Floro and the Kaupanes project in Egersund. Each site will install 20 megawatts of capacity using Nel's modular MC500 PEM platform, creating a combined 40-megawatt footprint. For Nel, this represents its largest order to date for PEM technology and its second-largest confirmed contract overall, marking a major milestone for the Norwegian hydrogen sector as it advances from pilot to early commercial scale. The MC500 system integrates electrolyzer stacks, power electronics, and balance of plant components in containerized modules. This approach simplifies logistics, reduces on-site assembly, and enables gradual scaling as hydrogen demand grows. Both facilities will draw renewable electricity from Norway's hydropower-based grid, ensuring low-carbon hydrogen output. Deliveries are planned for 2026-2027, with commercial operations scheduled for early 2028. The stacks themselves will come from Nel's automated manufacturing plant in Wallingford, Connecticut, one of the world's most advanced PM production lines, demonstrating the increasingly international nature of hydrogen equipment supply chains. Financing for these Norwegian projects follows a blended public-private model. Enova SF, Norway's state agency for climate and energy transition, awarded grants of 180 million kroner to HyFuel and 206 million kroner to Kaupanes. Such funding reduces upfront risk and aligns with the government's strategy to make renewable hydrogen competitive with traditional hydrogen produced from natural gas. For developers, this combination of public capital and private procurement provides a practical template for how early-stage infrastructure can reach bankable status. Similar models are emerging elsewhere in Europe, where state incentives bridge the gap between current costs and long-term commercial viability. The two sites were chosen strategically. Floru's maritime base provides access to offshore logistics and shipping applications, while Kaupanes offers proximity to industrial consumers and potential transport corridors. Both areas already have renewable power connections and space for future expansion. These projects are expected to serve as reference points for further Norwegian and Nordic hydrogen investments. From a cost perspective, the $50 million contract equates to about $1.25 million per megawatt for installed PEM capacity, including auxiliary systems. This figure reflects the sector's current pricing and shows how industrial automation and scale are gradually lowering capital costs. A few years ago, similar systems cost notably more. As global electrolyzer production expands, unit prices are expected to continue falling, reinforcing green hydrogen's competitiveness. The use of PEM rather than alkaline technology also highlights changing technical priorities. PEM systems handle variable renewable power more efficiently and can operate dynamically, providing grid flexibility in regions where renewable generation fluctuates. Although PEM remains somewhat more expensive than alkaline, developers like HYDS are choosing it for its rapid response and compact footprint, qualities that suit Norway's hydropower-dominated grid and maritime sectors. For Nel, this order validates its PEM product line and underlines its transition from pilot deliveries to large commercial batches. The project timeline, roughly 3 years from order to operation, demonstrates the planning horizons typical of infrastructure-scale hydrogen developments. Coordination among engineering, procurement, grid connection, permitting, and offtake arrangements is essential. Such multi-year cycles also emphasize the need for strong project management frameworks and financial discipline. Even with generous renewable resources and supportive policy, project economics depend on meticulous scheduling and cost control. Beyond Norway's borders, this initiative contributes to Europe's collective hydrogen goals. The continent aims to install at least 40 gigawatts of renewable hydrogen production capacity by 2030. Mid-sized projects such as HyFuel and Kaupanes are vital stepping stones. They generate operational experience, refine safety standards, and create data that inform the design of future 100 megawatt and gigawatt class plants. They also demonstrate how international cooperation, U.S. manufacturing supporting European deployment, can efficiently distribute production and expertise. While Norway strengthens its production base, Germany is advancing the upstream materials and downstream application layers that make these systems viable. Near Frankfurt, BASF Environmental Catalyst and Metal Solutions, ICMS, has opened a dedicated facility to manufacture key components for PEM electrolyzers and fuel cells. The Budenheim plant focuses on producing catalyst-coated membranes, the thin functional layers where hydrogen and oxygen separation occurs. These membranes rely on precise coatings of platinum group metals such as iridium and platinum. By establishing local manufacturing capacity, BASF is shortening a supply chain that was previously dependent on imports and lengthy logistics. The strategic significance of this facility lies in cost reduction, supply security, and sustainability. Catalyst-coated membranes account for a meaningful share of total stack expense, largely due to the cost of precious metals. BASF's goal is to optimize coating processes so that less metal is required without compromising efficiency or lifetime. Every reduction in grams of iridium or platinum per kilowatt lowers the cost of electrolysis systems and lessens exposure to volatile metal markets. Locating production within Europe also minimizes transportation costs, improves quality assurance, and supports the region's efforts to maintain technological sovereignty in clean energy hardware. The Budenheim site also integrates recycling operations that recover metals from end-of-life stacks, allowing a circular flow of critical materials. This approach reduces environmental impact and supports Europe's broader push for resource efficiency. From a project development viewpoint, such circularity can lower life cycle emissions and strengthen environmental social governance metrics, which are increasingly important to financiers evaluating hydrogen investments. Economically, localized component production can affect both capital expenditure and schedule risk. Developers depend on predictable delivery of stacks and membranes to meet construction deadlines. Shorter supply chains reduce the likelihood of project delays and currency exposure. As a result, contingency allowances in financial models can be tightened, improving project bankability. For policymakers, the Budenheim facility signals progress toward a complete European hydrogen value chain, one capable of supplying, assembling, and operating electrolyzer systems without external dependency. If BASF's initiative represents the materials foundation of Europe's hydrogen economy, Bosch's newly commissioned 2.5 megawatt electrolyzer at Bamberg illustrates the application layer, how hydrogen is being produced and used within industrial operations. At this site, Bosch installed 2 in-house developed PEM stacks, producing more than 20 kilograms of hydrogen per hour. The system runs on certified renewable electricity and meets the EU's renewable hydrogen rules by ensuring temporal and geographical alignment between power generation and hydrogen output. What makes this project notable is Bosch's dual role as both technology supplier and operator. By running its own electrolyzer, the company gains first-hand operational data on efficiency, degradation, and maintenance cycles. The hydrogen produced is consumed on-site for testing fuel cell power modules and other internal uses. This closed-loop configuration, known as a behind-the-meter setup, avoids transportation and compression costs, enabling cost-effective hydrogen generation directly at the point of use. Behind-the-meter systems like this can achieve competitive production cost when paired with reliable renewable power. With no network fees or grid tariffs, the effective electricity price is lower, and utilization can be optimized for internal demand. For industrial facilities seeking to decarbonize operations, such configurations provide an immediate pathway to emission reduction without waiting for large-scale hydrogen pipelines or external supply contracts. They also act as practical demonstrations of how hydrogen can integrate with manufacturing processes, energy storage, and quality testing routines. From an analytical standpoint, Bosch's Bamberg system represents a real-world case study in decentralized hydrogen production. It contrasts with large merchant plants designed for external customers. While centralized plants benefit from scale, decentralized units offer faster deployment, lower permitting barriers, and immediate operational benefits for the host facility. Over time, clusters of these smaller systems could connect into regional hydrogen networks, creating hybrid ecosystems that balance efficiency and flexibility. Comparing these German advances with the Norwegian projects reveals a continuum of progress along the hydrogen value chain. Norway focuses on generating renewable hydrogen at commercial scale using large PM modules. Germany is fortifying the upstream supply of membranes and materials while simultaneously demonstrating downstream integration within industrial sites. Each stage reinforces the other. As component manufacturing expands, equipment costs decline. As industrial users adopt hydrogen systems, market demand stabilizes. Together they form a feedback loop that strengthens Europe's position in the global hydrogen transition. For project developers, these examples carry several lessons. First, supply chain maturity directly influences project economics. The existence of advanced manufacturing capacity for critical components like catalyst-coated membranes reduces supply risk and supports more confident cost projections. Second, blending public funding with private procurement remains a key enabler for early projects. Norway's Enova grants illustrate how government support can de-risk capital-intensive infrastructure until economies of scale emerge. Third, decentralized deployments such as Bosch's show how industrial firms can begin decarbonization immediately, generating internal learning before scaling up to external markets. From a policy perspective, these projects align closely with Europe's decarbonization objectives. They strengthen regional manufacturing, create skilled jobs, and demonstrate practical pathways to meet hydrogen production targets while complying with environmental standards. They also highlight cooperation across borders. The Norwegian projects using US-built stacks, the German projects anchoring European component supply, and both feeding into a broader continental strategy for renewable hydrogen. As the sector advances, data from facilities like HyFuel, Kaupanes, Budenheim, and Bamberg will feed back into future designs. Performance metrics, maintenance intervals, and efficiency results will refine cost models and investment assumptions. The more reference projects that operate successfully, the stronger the confidence of lenders, insurers, and off-takers becomes. Over time, this accumulation of empirical evidence will help the hydrogen market evolve from grant-driven to fully commercial. In essence, Europe's current phase of hydrogen deployment is defined by these complementary moves: scaling production capacity in the north, deepening supply chains in the center, and embedding hydrogen usage in industry. The outcome is a more resilient, interconnected hydrogen economy. Norway provides proof of commercial feasibility for mid-scale renewable hydrogen plants. Germany provides the manufacturing depth and operational examples needed to sustain and replicate that success elsewhere. For analysts, consultants, and developers following the market, the takeaway is clear. Progress in hydrogen is not happening through a single breakthrough, but through the coordinated advancement of multiple layers: materials science, equipment manufacturing, project financing, and end-use integration. Each project, whether a 40-megawatt electrolyzer cluster, a membrane coating plant, or a 2.5-megawatt industrial system, contributes data, confidence, and expertise that move the sector forward. At this stage of the energy transition, these steps may seem incremental, yet they collectively form the foundation for the large-scale hydrogen economy envisioned for the 2030s. Europe's mix of policy support, renewable resources, and industrial capability positions it well to remain a leader. As more plants come online, costs will continue to fall, technology will mature, and green hydrogen will become a practical, deployable part of the continent's energy system. For those seeking structured insight into how such projects are conceived, financed, and executed, further guidance on feasibility studies, permitting frameworks, and financial modeling approaches is available through reneenergy.com and H2 Hub. reneenergy.com, platforms dedicated to supporting professionals developing the next generation of hydrogen projects.